Okay, we're going to be talking about a rather important topic, the partial derivative. So, this is one way of extending our notion of derivative from Calc 1 to Calc 3. There's going to be another related notion called the directional derivative that is built on top of the partial derivative. But we're going to start here with partial derivative. So, Um, the main point is that in Calc 1, we had only one direction that we could change our input variable. We only had one input variable, x, and we would compare, um, I guess I don't have the difference quotient written here, but you can remember, let me see here. I should have written it somewhere, but okay, so back in Calc 1, you learned that this was defined to be the limit as h goes to 0, f of x plus h minus f of x all over h, right? That is the way that we defined the derivative of a function. We ended up adjusting x by a small quantity and then taking this difference, this change in y over change in x. That was the idea. And for Calc 3, we have to just adjust this in order to factor in the different directions that we can adjust. So since we now are dealing with, well, functions of 2 variables and 3 variables, but this actually can easily generalize to however many variables you're dealing with. The idea, the main point of the partial derivative is we only change the derivative, or we only change, we treat the variable that we are taking the derivative with respect to is the variable that we end up changing, varying. And all the other variables we leave as constant. We pretend that they are constant. We treat them as some fixed values. Okay, that is how the partial derivative works. So if we look at the definitions here, and I guess I need to also comment that how the notation works. So with the ordinary derivatives, we had a straight d. With partial derivatives, we have these curly d's. These are also called partials. So, but I'm probably going to commonly just pronounce this as d. So this is df dx, and this is df dy. But the curly d, this partial symbol, represents the fact that we're talking about a function that has more than one variable. So it means we're only varying the x, but we're leaving the other values, the other letters, as constant. And I'm also kind of introducing the fact that there are other notations that can be used for partial derivatives, such as this subscript notation. So this subscript is saying we're taking the x derivative of the function f with y derivative of the function f. But here it's kind of I don't think that this notation was ever used in Calc 1. I guess we normally just used primes, but here it's because, well, the function f might have more than one variable, so we have to specify which derivative, or which variable we're taking the derivative with respect to. Okay, and so, like, yeah, look at this definition. So here we're saying that the function f is a function of 2 variables, x and y, and for this derivative with respect to x, we end up adjusting the x by a small quantity h, and we're taking the difference. And then we divide by h, and we take the limit, which is kind of the same as the difference quotient, the way that we define limit in Calc 1, except we only vary the x component for the partial derivative with respect to x. And then similarly, with the partial derivative with respect to y, we vary the y component. Instead of h, I end up using k. I think I'm following the definition that the book provides. But yeah, here we only adjust the variable y. We don't touch x at all. Okay. And if we had more variables, if we're working in dimension 3, then you might have df dx, df dy, and df dz, and the statements generalize in pretty much the obvious way. So with an additional z component, you don't touch z if you're taking an x derivative or a y derivative. So you see that the x derivative, you only adjust the x. The y derivative, you only adjust the y. The z derivative, you only adjust the z. So really, these partial derivatives are capturing the amount of change if you adjust in that particular direction or with respect to that particular variable. Right? If I increment my z by a small amount, how much do I expect the function f to change by? And similarly with all the other variables. Now this is the abstract definition. I think we'll shortly get to how we actually practically use this. And the idea is just going to be that we can end up using all of the old derivative rules from Calc 1. But I guess I first have... Oh, so I don't even really mention it here. That's... yeah, okay. I mentioned it in this boxed statement. So with partial derivatives, you treat all the other variables as constant, and then you can use the derivative rules that you're already familiar with. And we'll see a few examples involving this. But first, this kind of visual example. So calculate the sign of the partial derivative using the graph. Right, so in this graph, you can see that the point 1, comma 1 is, maybe I need to draw this, but like, yeah, the point 1, comma 1 is over here. It's kind of there on the surface, kind of in the back half, the right side of it, I guess is how you might describe it. And so if you're talking about the derivative in the x direction at this point, so that's what happens if you adjust by x a small quantity, which means that we end up moving to the right a little bit like this, as I'm pointing out on the screen. Well, you can see that this the function is then going to move me up, right? My z coordinate goes up a little bit, so this this quantity is positive. And same with if I move in the y direction. So moving in the y direction, I end up moving further back, and you can see that the shape of this surface, it's moving, the z coordinate gets moved up as well. Okay, versus, well, so the thing is that with these, you're always moving x in a positive direction or y in a positive direction. I guess the other possibility would be like if I was back here at this point, then moving in the positive x direction, I see my z goes down. Moving in the positive y direction, that's not positive y. Okay, over here, if I move in the positive y direction, my z goes down. So, yeah, hopefully you can follow that. Okay. So calculating partial derivatives is the next thing here. So suppose you have this function and you're asked to take the derivative with respect to x, the derivative with respect to y. So you should hopefully remember that the derivative of the log function, the way that you do that is you put the inner function into the denominator and you follow that up with chain rule. So we have all of the rules of derivatives from Calc 1. All of those carry over. We just have this additional thing we do with other variables. We pretend that they are constants. So just like pretend that it's a number and proceed as you would normally. So when you take the derivative with respect to x, you notice that yes, this ln is a function of x, so you use the logarithm rule. So that puts this in the denominator, and then you end up taking the derivative of x to the 6th power, which follows a power rule. This is treated as a constant, so the derivative of a constant is equal to 0, which means you can disregard that. So you end up just having 6x to the 5th, which is there. Next, for the dz dy, again, this function, this is a function of y, so when you take the y derivative, you first start with the derivative of the logarithm function, which puts the inner function into the denominator. Then you take the derivative of the inner function because of chain rule, and because we're taking the derivative with respect to y, this x to the 6th is treated as a constant. derivative of a constant is 0, so we can ignore that part. And we only have this to consider. This, when we take the derivative with respect to y, we get 4y cubed because of power rule. And so we get that. And so that's how we get these two answers. Let's see what else we've got. I guess I just try to give another example of a calculation. So yes, so with both of the dz dx and dz dy, tangent, you would end up having a secant squared, right, for both of them. The inner function stays the same, and going a little bit fast, I'm combining these things. So with chain rule, right, you see that the x derivative, it's just only going to capture this part. This y is treated as a constant with respect to the x derivative. And so you end up just having 2 as part of the x derivative. With the y derivative, the 2x is treated as a constant. You just have this minus y. So the y derivative gives you a minus 1. And so I've written it like so. Okay. Well, we also have the notion of taking higher derivatives. So derivative of a derivative can also be done. So I have to talk about the notation a little bit more because there's sort of there's an ordering kind of issue. The order that these things show up is reversed in the two different ways of writing these things. So with this subscript notation, it's read left to right. So this is you take the x derivative, then the y derivative. This you take the y derivative, then the x derivative, right? As you would expect. I think you would expect that. But this other notation, it ends up being reversed. And the reason is actually this middle column. So notice that the x derivative followed by the y derivative would be written like this. You take d dx of f followed by d dy of that function. And then we, the notation, it's kind of abusive notation. What's going on here is that you just kind of squash the fractions together, and that ends up keeping these variables in the same order. But you see that the variables end up being out of order. So this is xy, but this is yx. You have to, when you have the partial derivatives written in this way, you technically are supposed to read things from right to left, because the rightmost derivative is being done first, because it ends up unpacking in this way. Right. The xy and the yx are called mixed partial derivatives because they end up using different variables. So the reason I said that technically you're supposed to do it in this order is because you end up having this useful theorem called Clairaut's theorem, which says that in fact for I guess I should say for nice functions, in particular, nice means that the functions are the derivatives, I should say, the mixed derivatives of the functions are continuous on some domain. Then you know that these mixed derivatives end up actually being equal. Okay. And so you can basically expect that for whatever functions you encounter, this is going to hold true. Like, only in weird circumstances does it not hold true. So, yeah, you can basically assume that the mixed derivatives are going to be equal due to Clairaut's theorem. Although, I guess I do treat one of these problems as though that's not the case, just to kind of to verify. And I think I didn't modify your problem too much from this point. I think your problem was also of this nature, more or less, of verifying Clairaut's. I don't remember exactly. So yeah, say you have this function, and the problem basically was asking to compute the mixed partial derivatives, the dy dx, or no, not dy dx. The how do you say that? I don't know, the xy derivative and then the yx derivative. I guess is how you could say that. So you start by taking the first order partial derivatives, then you compute the second order ones, some of the second order ones. You don't need to compute xx or yy. We will need those eventually. They do also come into play in a formula, but that'll be later on. So, okay, let's talk through this just as additional practice, getting used to partial derivatives. So, hold on a second. Oh, the way I rewrote this is not so great because there's also an additional z. It would not be clear initially that, yeah, in this problem, there are actually going to be like 6 mixed partials because there's 3 variables. Oh well, ignore that. So yeah, so just pretend the problem is like just to verify that these two are equal. So the x derivative, let's see. This sine function is not dependent on x at all, so this is treated as a constant with respect to this derivative with respect to x. We only have this exponential function to deal with. Derivative of this exponential is going to pull out a -2. So we get a -2, the exponential, and then the sine. That's the x derivative. The y derivative, so now this exponential is treated as a constant. It doesn't vary when we vary the y variable. Okay. The sine function does vary when we change y. So we end up taking the derivative of the sine, and z squared is going to be treated as a constant. So that's going to come out. So let's see. Yeah, the exponential is a constant. The sine's derivative is a cosine, and then we have a chain rule where we take the derivative of the inner function, and the z squared is treated as a constant when we differentiate with respect to y. So we have that. Okay. And then in order to compute these mixed partials, well, for this one, I have to take the x derivative of this function. And I think you can see that this part is all constant with respect to x, the x derivative. And the x derivative is only going to pull a -2 from the exponential. So we end up with this. For this mixed partial, we have to take the y derivative of the x derivative. So we take the y derivative of this, and you can see that the exponential is constant, the sine becomes cosine, it's going to pop out a z squared, which gives you this expression. Exactly. Okay, and I think this is the last example I have here. So, I don't know, fun little example, I suppose. So you can take really high order derivatives if you want to, or if you're asked to, I guess. So the x, y, z derivative. So we do this from left to right, because that's how this notation works. So first we take the x derivative. You can see that the z and the y are treated as constant. We only think about the ln of x. We take that derivative, which gives me 1 over x. So we end up with this. We then have to take another x derivative. So this I think of as x to the negative first power. So I use power rule, which gives me minus x to the negative second. So that's a x squared in the denominator. Next, we have to take a y derivative. So then y squared becomes 2y. All the other variables are treated as constant, giving me this. And then I take 2 z derivatives. So we have a z cubed here. That's going to become 3z squared, give me a 6z squared. All the other variables are constant, treated as constant. And the second z derivative, the z squared becomes 2z. So we end up with the final expression. And so that's how we deal with these partial derivatives. So I know that this ends up being a bit confusing if this is your first time looking at partial derivatives. You'll want to do some practice to get comfortable with it. Get used to like viewing other variables as being constant. It's slightly different. All right.